In this screencast, we're going to look at elementary matrices. The idea is we start with the identity matrix and perform a single row operation. These are the 3 row operations. I just want to show you an example. We start with the identity. So the identity, we'll just work with some 3 by 3s. This idea works on any size matrix. But you start with the identity, and now you could interchange 2 rows. So if I interchanged row 1 and row 2 and swapped them around, then the idea is I'd get 0, 1, 0, 1, 0, 0, 0, 0, 1. This is an elementary matrix. Now, you can also multiply a row by a non-zero constant. So I could take, say, row 3 and times it by 4. So if I take row 3 and times it by 4, I start from the identity and I times row by 3 by 4, which gives me 1, 0, 0, 0, 1, 0, 0, 0, 4. That is an elementary matrix. I could also take, say, row 3 and let's add negative 4 times row 1. Remember, I do that to the identities. So row 3 minus 4 of those would give me the matrix 1, 0, 0, 0, 1, 0, minus 4, 0, 1. These are all examples of elementary matrices. You are allowed to do one single row operation. So some comments with these. We've got the matrix 0, 1, 0, 1, 0, 0, 0, 0, 1. This first type, if you look at determinants, notice that we flopped 2 rows, which means the determinant's negative 1. We just switched the orientation. The inverse is also, if I want to undo what I just did, I can flip the 2 rows again. And you can check by multiplying them together that you get the identity out. We'll also look at the next one. We've got this 1, 0, 0, 0, 1, 0, 0, 0, 4. If the elementary matrix is formed by multiplying row 3 by 4, well, the determinant, it's just the product of the diagonals, is 4. It's whatever I multiplied by. And the inverse? Well, if I want to undo that, I should divide by 4. And that gives me precisely the inverse. And with the last one, where I have the 1, 1, 1, and then a negative 4 in the bottom left, here, this was add negative 4 times row 1 to row 3. If I want to undo that, the inverse would be let's add 4 times row 1 to row 3. And so inverses are really simple for elementary matrices. So are determinants. Here, the determinant product of the diagonals is 1. Notice all of these cases, the determinant will always be 1. Anytime you switch 2 rows, the determinant's negative on it. And anytime you multiply a row by a constant, it's whatever that number is. That's the determinant. Inverses are just undo what you did. That is what an elementary matrix is. Now, why do we even care? Well, suppose you start with some matrix A, and let's have the matrix be 1, 2, 3, 0, 1, negative 2, and 2, negative 1, 3. Well, if I call this E1, I'll call this one E2, and I'll call this one E3. What is the product E1A? E1 was formed by switching row 1 and row 2. Well, what's E1A? If I multiply them together, I'll just write them out. 0, 1, 0, 1, 0, 0, 0, 0, 1. And then we've got our 1, 2, 3, 0, 1, negative 2, 2, negative 1, 3. Well, the idea is, remember that matrix multiplication can be done by taking linear combinations of the rows using this row as the coordinates. So 0 times the first row plus 1 times the second row plus 0 times the third row will give me the first row, which really means I take this row and put it on top. 0, 1, negative 2. This one says take 1 times the first row and none of the other 2 rows. And now this one says take the third row and just leave it there. Well, hold on. That was just switch the rows. So multiplying by E1 just swaps the rows of A. Similarly, if I take E2 and times it by A, well, E2 was 4 times row 3. I'm just going to cut to the chase, and really that just means let's take row 3 and multiply it by 4. Leave row 1 there, leave row 2 there, and multiply row 3 by 4. So we get a 1, 2, 3, 0, 1, negative 2, and then 8, negative 4, 12. In other words, multiplying by the elementary matrix does precisely that row operation on A. Similarly, E3 times A is, well, here it was take minus 4 times row 1 and add it to row 3, which, if we now take this row times A, then it's 1 of that row, 0 of that row, and 0 of that row added up, which gives us our 1, 2, 3. 0 of the top row, 1 of the middle row, and 0 of the bottom row. So 0, 1, negative 2, and then minus 4 of these. So minus 4 of 1, 2, 3, plus 1 of 2, negative 1, 3. Wait a minute, that's exactly the same thing as doing a row operation. So row operations are the same as multiplying on the left by an elementary matrix. So one thing that means is if A eventually row reduces to the identity matrix, suppose A reduces to the identity matrix, well, then that means I could take A and I could multiply on the left once, do the first row operation, on the left twice by the second, again by the third, again by the fourth, and I could produce a whole sequence of row operations. I may have to do a bunch, but eventually I'll get out the identity matrix. Every single row operation is just another multiply on the left by another matrix, which means if I wanted to, I could solve for A by multiplying by the inverse of this matrix. You remember the inverse is you flip the order and invert each one. So you can actually solve for A as, let's flip the order and invert each one. E1 inverse, E2 inverse, E3 inverse, E4 inverse, up to En inverse. In Shams, they'll have you actually work out one of those in some of the homework. That completes this screencast.